So, last time we just introduced Chapter 1 and
Mic off.
parts of Chapter 2. And so, what do we remember about last time? So, last time, what are some of the things that we talked about? Well, we talked about, as we go back up to the beginning of Chapter 2, we talked about work, kinetic and potential energy, which is right here. So, kinetic energy. Then we have potential energy, which is a little further down, which is right. Potential energy, which is right here, and how it is represented in terms of this class. So, this right here. We also talked about very important definitions. So, back up real quick. Very important definitions, which are, we had system, which is the area or the thing that you're working on. So it's what is the system in front of you. So, for example, my system could be my desk, right, in front of me. So you draw a boundary, which is the next thing. A boundary is outside of the system, right? It's the thing that it separates the system from the surroundings, right, is the boundary. And the surroundings is everything not in the system. And then we have a closed system. A closed system is something like water inside of a water bottle, and you screw the cap on. Mass is not allowed to flow in or out of it, right? It's just whatever's inside of it is what it's going to be from one state to the next. And then a control volume is the other version of that, which is mass is allowed to flow through the boundary layer. So essentially it's essentially able to flow through it. So you can have mass coming from outside to inside and then leaving again. Alright, and then we have a property. A property is essentially something that describes the fluid or whatever is going on, like so temperature, pressure, volume, things like that. It's something like that describes what is going on at each state point. And there are two types of properties. There are intensive and extensive properties. And so, extensive properties, if I recall, I have to make sure I don't flip these two because I often do. But extensive, I'm pretty sure, is the one where, let's go back up. I might as well make sure I get this right so I don't mess this up. Here it is. So extensive properties are ones that depend on the size of the system. So, for example, mass depends on the size of the system, right? Because if the system's bigger, you have more mass, right? Intensive properties do not depend on it. They depend on solely, basically, they depend on something that's not related to the size of the system. So, for example, temperature, right, does not depend on the size of the system, right? So, like, if there's an object in front of you, the temperature could be, it could be differences, right? It could be differences in, I think we talked about it right here. It could be differences in temperature that are unrelated to how big the system is, right? So those are the two types of properties. Now we scroll back down. One sec. Oh, we have another student join the class. Give me a second, guys, before we continue. I didn't know he was in this class as well. He must have just joined. Alright, so he should be able to join now. Yes, welcome, Luke. So really quickly, we were just going over what we talked about last time. Don't worry if you missed it, because I record all the lectures for this class. So the first lecture is already online, so you can go through and watch that on your own time. Alright, so then the rest of this stuff wasn't really things we had to worry about. The only other things I would say is specific volume, which is an important concept in this class, is the inverse of density, and it is often used to describe or help us find things about the question, or to locate state points. I guess I should talk about that too. So states, if you recall, state points are essentially things leading up to a process. So, for example, at one state, your water could be liquid, and then it could go through some process, and it could all of a sudden be steam, right? It could be vapor. And so that is a process is something happening in between two state points. And then obviously you guys know these right here: pressure, temperature, Kelvin, Rankine. So we don't really need to get too far into that. So now we can pick up where we left off. So where we left off was right here. So this was the sign convention. We left off right here, but I'm going to get back to this as well. So the sign convention for work. So really quickly, once again, work that is done by the system. So for example, if you are getting something out of the system, right? Like for example, let's say the system is making work, like your car, for example. Your car, for example. If you join the stream, Luke, you can see what I'm doing right now. So click on my name and join. But essentially work by a car, right? So the piston cylinder arrangement is making work. Inside of that system, there is some explosions going on, like some combustion process, and then power is being translated down to the wheels, right? So work is leaving that system. Network is leaving that system. Therefore, that is work done by the system, because the system is doing work and creating it for us, right? Somewhere else. Work done on the system is whenever we have to put something in, right? So when there has to be external work put in, that is done by on the system. So here's an example of that. So in your air conditioning unit, your compressor has to be, essentially it has to be ran by electricity, right? So we are having to input electricity for the compressor to work in your air conditioning unit. So therefore that is work done on the system. Your compressor is not creating work. It is not being used. Your compressor doesn't power other things, right? It requires power. So that's the difference. And so, really quickly, once again, work done by the system, positive. Work done on the system, negative. Luke, did you end up joining the stream? You just have to click on my name and then join stream. It says there's only 6 people in here, so it might be you. Anyway, so we can move on. And so, really quickly, work for us is that essentially... Here, let me go back up a little bit here. So as I said, work is not a property from last time. The limits, so in addition, the limits on the integral of equation 2-2, which is, I think it was shown a little earlier, but I think this is essentially it right here, is that mean from state 1 to state 2. So essentially the limits on the integral are state 1 to state 2. They are not anything else. So for example, it's a process. So essentially what we're looking at is the work of a process. And it says, and cannot be interpreted as values of work at these states. The notion of work at a state has no meaning, so the value of the integral should never be indicated as work 2 minus work 1. So don't ever think of it as that. Think of it as work 2. Basically, what is the difference in energy from one state to the next? That is the work. So right here, this is sort of, you have to this is an equation you should remember, and it'll pop up very soon again, but we'll get to that. So real quick, let's talk about power. So it says many thermodynamic analysis are concerned with the time rate at which energy transfers occurs. The rate of energy transfer by work is called power, and is denoted by W dot. So W dot is power in this instance. So W dot, right? And it says, when a work interaction involves a microscopically observable force, the rate of energy transfer by work is equal to the product of the force and the velocity at the point of application of the force. So essentially it is F times V. And it says a dot appearing over the symbol, as in W dot, is used throughout the book to indicate a time rate. So for example, if there is no time rate, then there is no dot. But in this instance, we are talking about a dot. Okay? And then it says, in principle, equation 2.13 can be integrated from time 1 to time s, so the next time, to get the total work done in that time interval. Or you can integrate over 2 state points, and there is no w dot, because it's not time based, it is state based. It's from one process to the next. And that's what we'll be working with first. Time intervals will not be something we do first. It'll be the no dot one, which is fine. I mean, if you mess that up at the beginning, it's not a big deal. And then it says the same time convention applies for w dot as w. Since power is a time rate of doing work, it is expressed in terms of any units for energy and time. In SI, the unit for power is a joule per second, which is a watt, or a kilojoule per second, kilowatt. And then English units for power are foot-pound force per second, or BTUs per hour, or horsepower. English units are kind of messy like that, but that's the way it goes. Alright. So now let's move on to something that this is basically, so everybody right here, this is the beginning of problem solving in this class, is what we're about to talk about. The other stuff was just things that you need to know beforehand. This is where we start to get into some things that involve problem solving. So this is the time to turn on your brains for just a minute. So I just said just a minute though. So right here we have modeling expansion or compression work. So it says there are many ways in which work can be done by or on a system. The remainder of this section is devoted to considering several examples, beginning with the important case of work done when the volume of quantity of a gas or liquid changes by expansion or compression. So it says, let us evaluate the work done by a closed system shown in figure 2.4, which is this right here, consisting of a gas or a liquid contained in a piston cylinder assembly as the gas expands. During the process, the gas pressure exerts a normal force on the piston. Let P denote the pressure acting at the interface between the gas and the piston. The force exerted by the gas on the piston is simply the product PA, where A is the area of the piston, so it's pressure times area. The work done by the system as the piston is displaced a distance dx is this, PA dx. And then it says the product A dx equals the change in volume of the system dV. Thus, the work expression can be rewritten as this, which is work is equal to PdV, more or less. So what we're getting into, this is the equation. This is a lot of derivation, but this is what we're looking at. This is the equation you need to remember, is that work is equal to the integral of PdV as you take it from the limit of volume 1 to volume 2. Okay? Does everybody understand that? That this is the one that you really need to know. This other stuff is just derivation. It's this equation right here. This is the important one. So it says, for a change in volume from V1 to V2, the work is obtained by integrating that equation. And then it says, although equation 217 is derived for the case of a gas or liquid in a piston cylinder assembly, it is applicable to systems of any shape provided the pressure is uniform with position over the moving boundary. Okay? Now we can move into actual processes, but let me see if there's anything else I missed before we do that. Nope. Okay, moving on. So, it says expansion or compression work in actual processes. So let me see if there's anything here that is. Okay, so most of this is kind of not really important, but this last part is essentially it's saying that performing an integral of equation 217 based on a curve fitted to the data could give a plausible estimate of work, which is what we are actually we're doing, right? It says we'll see later that in some cases where lack of pressure or required pressure volume relationship keeps us from evaluating the work from equation 217, the work can be determined alternately from an energy balance. So that is later. So the energy balance part is later. What we are doing now is that we are doing work relationships using this first equation right here. But what that means is that we cannot find the work unless we know the relationship from pressure from the one state to the next, right? And so, because we have to know that relationship, it makes it difficult if you don't know that relationship. But you will be given that mostly in this section. So let me see if there's anything important here. I don't think there's... Okay, there's something in here that is important. So, it says, a graphical relationship is shown on the pressure volume PV diagram of figure 2.7, which is right here. Right? So this is a PV diagram. So this is pressure on the Y, volume on the X, right? And it's saying that at each intervening piston position, the uniform pressure throughout the gas is shown as a point on the diagram. The curve or path connecting states 1 to 2, which is right here, state 1, and state 2, represents the equilibrium states through which the system has passed during the process. The work done by the gas on the piston during the expansion process is given by the integral of P dV, which can be interpreted as the area under the curve of the pressure versus volume. Okay? So, what it is saying is that the work can be considered the area under the curve here. But you're not... we're not... That's like, that's some calculus things that I don't know if you guys are familiar with. I'm sure you are, though, at this point. But that's more for your knowledge, not so much in practice. You will be doing integrals, which is the area under the curve, but that's more, derivation. All right. And then it says, thus, the shaded area on figure 2.7, which is here, is equal to the work for the process. So, right here is the work. At least I do believe so. Make sure that's what they were exactly meaning. There's some shaded areas on both of them. Thus, can be termed as the area under the curve for the pressure versus volume. Thus, the shaded area on figure 2.7 is equal to the work for the process. Had the gas been compressed from 2 to 1 along the same path, the magnitude of work would be the same, but the sign would be negative. So that's the important thing I wanted to get to, is that essentially the direction of the work, so negative or positive, is dependent on the process being done. So for example, let me draw a little cylinder here. You guys are probably going to laugh at my very poor drawings. But let's say we have a cylinder here, and this is the piston on the inside, right? So if this is the piston on the inside, if the piston is here, right? Let's draw it the other way around. That's probably better. If the piston is at the top, right? And then on the next one, this is the second state, right? This is after the piston has moved from here. This right here shows a positive work because the gas up here expanded the piston, right? Essentially, it pushed the piston down. And because the gas pushed the piston down, it means that the gas created work. Essentially, it created a positive work. It pushed it down. We did not have to push it down. We did not do anything to push the cylinder down, right? The gas did it on the outside. There was no, let's put it this way, there was no exterior work that we had to put in here to get this piston to move down, right? Now, if it was the opposite way, which means that last case was positive, if it was the opposite way, like this, and then at the second state it was up here, well, very clearly we had to do something to get this piston to rise, right? You see what I'm saying? This piston had to go from here to up here, which is a higher pressure, right? Because we've limited the volume. So that means there had to have been some work input here, which means that the work created from this section is negative. This is a negative work because we had to do something externally to get the piston to rise up. The previous case, the piston was pushed down by the forces inside of it. Therefore, it was a positive case. So that's sort of where we're going with how to do piston cylinders for your sign convention, right? So that was the important part of this section right here, was to know that. All right. And now this right here, this is the part that is important. And this is where you start your problem solving. So it says, the relationship between pressure and volume, or pressure and specific volume, can also be described analytically. A quasi-equilibrium process described by P to the V, PV to the N equals constant, or P specific volume to the N equals constant, where N is a constant, is called a polytropic process. Additional analytical forms for the pressure-volume relationship also may be considered. The example to follow illustrates the application of equation 217 when the relationship between pressure and volume during expansion is described analytically as PV to the N. So this right here is our first section's questions, is PV to the N. So you will be using this PV to the N in this first section. So do pay attention to that. This is how you will be solving your question. So essentially what this means is, earlier I said that you cannot do those integrals unless you know. You can't use that integral work is equal to PdV. You can't do that unless you know the pressure-volume relationship between states. This equation is giving you an analytical way to know the pressure-volume relationship between states. Right? So this is how it's telling. This is basically, they're giving you the relationship here. If we did not have this relationship, you would not be able to do it. So, really quickly, we're going to do a little bit of an example here. So, we have this. It says a gas in a piston cylinder assembly undergoes an expansion process for which the pressure relationship between pressure and volume is given by this. So, if you see this type of question, it says the relationship is given by this right here. That means it is a polytropic question. Polytropic process, okay? So this should be alarms going off in your head. If it tells you have to use that relationship, it's polytropic process. And then it says the initial pressure is 3 bar. So we would go P1 is equal to 3 bar. But really quickly, I do recommend that you turn bars into kilopascals, because kilopascals are easy to move into force units or work units. So 300 kilopascals. And then it says the initial volume is 0.1 meters cubed. So V1 is equal to 0.1 meters cubed. Okay? And the final volume is 0.2 meters cubed. Okay? So final volume, V2, is equal to 0.2 meters cubed. Okay? And it says determine the work for the process in kilojoules if A is equal to 1.5, 1, or N equals 0. So let's just pick one of these. Let's do, these two cases make it really easy, right? So really quickly, the 3 cases that you will probably receive are the following ones right here. Essentially, you will have one that is not 1 or not 0, 1 and 0. So let's do A first. Let's just do A really quickly up here. So, if you know that PV to the N for one has to be equal to the other, what you can end up doing here is you can set these equal to each other, and that is what you should do. So you would do P1 V1 to the N is equal to P2 V2 to the N, right? And so if you do that, you can go through the checklist over here and see what you have, right? So, if you know everything, so let's look at this. We know pressure 1, we know volume 1, and we know volume 2, right? So that means the only thing we can, and we also know N because in the question it's given it to us right here. It's given it for 3 different cases, so this is 3 different questions. If you solve around and find pressure 2, this is what that is the first step of this question, is to find pressure 2. And I wonder if they do it next. Let me see. Yeah. So I don't have to write it. But essentially right up here, because my writing will probably end up being bad. And so this right here, so there's 2 different ways you can do this question, and I don't know how I recommend you to do it. But So the problem is that there's equations you can memorize, and that is like one way to do it. And so for the first step, P is equal to constant over V, right? So that is sort of where we ended up here. So we have P1 is equal to V constant, so it was C over V, right? When you manipulate that initial equation. C over V, right? And if you do that, you end up with the following. If you integrate, you end up with the following right here. So really quickly, this right here is this is important. This is what you need to remember okay, I'm going to try and make this easy because explaining it other ways always confuses people. And I might be doing that anyway. But let's just do this really fast. So for n is equal to, if it's not equal to 1 or 0, your integration will look like the following. It'll look like that. So for example, if you can literally just throw your numbers into there. So let me, so essentially it'll be is equal to work is equal to P2 V2 minus P1 V1 over 1 minus n. So everyone write that down. I'm going to try and, because explaining it the other way always just confuses people. Because this is the derivation. If you want to know more about the derivation, it's right here. Essentially what they did was they did P, they replaced pressure in here with the constant over V to the n. And when you integrate this, you end up with this. And then constant can be then equal to P times V to the n. And then you replace this in here. And when you multiply that out, you end up getting this. So it's just derivation, but right here is what you need to know. So for n not equal to 0 or 1, that is what your integration will look like. So 0 or 1. That is, you could basically just skip the integration part and just get this. So everyone should be happy about that. Now, when n is equal to 1, you go down to the next step, which I don't remember if they did 0 first or 1 first. Yeah, they did 1 first. Okay. So the next one is logarithmic integration. So it's right here. Essentially, you have work is equal to, because they pulled out a constant. So you have, this right here. This is what you need to remember, is this. It's the same exact thing, except they did it with logarithms, or natural logs. So work is equal to P1 V1 ln H ln, I got ahead of myself, ln of V2 over V1. So basically what I'm giving you is these are the shortcuts to your these are the shortcuts to these questions when you have to find the work for a polytropic process. It's just this. So if you have n equals 1, n equals 0, n equals anything other than 1, this is what you just plug in. So you just have to know what case you have. If you see that your n is equal to something other than 0, 1, you just say work is equal to this. And then it's your job to find these other things, right? If you know n is equal to 1, it's just this. And then let me go write the other one. So n equal to 0. That means you just plug in P is equal to P. Pressure is constant. If I recall, is that one. Let me see if I'm right. Where'd they do that one? Yeah. So it says for n equals 0, the pressure volume relationship reduces to pressure equals constant, and the integral becomes work is equal to pressure times the change in volume, because the pressure stays the same. So essentially work is just a relationship of volume changing times the pressure, right? So these are the three cases, right? And if your question says the relationship is, let's say, use n equals 1, you will use this one. If it says n equals 1.2, you'll use this one. If it says n equals 0, you'll use this one, okay? And these are all derivations of the original equation, which is this right here. They just plugged this in and rearranged it in the integral, and then they did integration by logarithms, and then the other one was just a pretty simple integration because pressure was constant. So hopefully that makes a bit of sense, because you know these are things that we do need to know. All right, and then really quickly, just to show, let me see if I can scroll in here. So for the first one, as you see here, is they did this integration and they got to that. Then they plugged in all their values, which were they plugged in all their values, and so they don't have P2 though. If you recall from our initial unknowns, we do not have the second pressure. So it says to evaluate W, the pressure at state 2 is required. This can be found by using this equation right here. So essentially, remember, I told you that you have to rearrange that first equation to find pressure 2, and that is pressure 2. So they did P1, V1, and then they separated and got pressure 2 and brought this over here. And what they eventually found is that this is pressure 2. And if you recall, our initial pressure was what? 3 bar? Is that what they said? Yeah, it was 3 bar. And what that means is that our pressure got smaller by a factor of 3, which means that our piston expanded. And so think about it in your head, though. Think about that. So if the piston was really pushed up and had a small volume, it means that the pressure had to have been high, right? So think about like a plastic water bottle. If you twist the top of it and like cut off the bottom, essentially you're making the volume smaller, and that's why at the top it feels like it's really, really tight. Right? Volume got smaller, same amount of mass in there, higher pressure. But then when you release it, it expands, and the pressure dropped back down to 1, which means that it expanded downward. And what that means is, remember from our original definition of work, if the piston was expanded by the gas inside, that means that work is what? Anybody want to answer that? Work is what? If the piston was expanded by the gas did work on the system, or it did.
It's positive.
It's positive. Thank you, Michael. And so, as you can see right here, work is then equal to, they just plugged this in right here, which is, this is pressure 1, volume 2, or pressure 2, volume 2, minus pressure 1, volume 1, divided by 1 minus 1.5, which is this, remember, it was this work equation right up here. And then you get a plus 17.6 kilojoules, which means that it was a positive number, which is right. It should be positive because the piston the piston was acted on by the force rather than it having to be pushed up by something else. And then you can see this example applies for all the other ones. Once again, this one was the one where n equals 1. We then plugged the exact same thing into here, which is that first equation, which is right here. So pressure 1, volume 1 times the natural log of volume 2 over volume 1, which is what they did here. Pressure 1, volume 1, and then they did some conversions because, like I said, guys, you want to put it in kilojoules, if you put it, kilopascals. If you put your pressures in kilopascals, you don't have to do this stuff right here. So it's very beneficial to put your pressures in kilopascals right at the beginning, because essentially what you would get is if you did it in bar, you would get like 0.279, which is not right. So you want to have your pressure in kilopascals, which if you need the conversion for that, 1 bar is 100 kilopascals. So obviously 3 bars, 300. That's not an exact one because I think it's 101.3 something, but let's put it this way. If you do 100, I'll be fine, okay? Not that concerned with it. And so right here, they get the same, they get a different answer, right? Because remember, this one had a different relationship for pressure and volume. So the answer should be different. And then the last one is kilojoule, is just 30. Because it was a very simple relationship. So I'm going to go ahead and write this off the screen. But those are the equations that you will need to know for, and these will be on an equation sheet always provided to you. You will not have to memorize any equations. So, good for you. Alright, let me see if there's anything else I have missed here. Alright, so then we have further examples of work. That concludes the last section. That was pretty much what we had to do here. Let me see if this is... this is something that we never work with. Yeah, this is nothing that we've never worked with in this class, so I'll just go ahead and skip that. Yeah, these won't be discussed in the course, so I can move by these. Alright, right here. So, broadening our understanding of energy. So it says, so that pretty much covers the work part, but essentially what we are now going to talk about is energy. In a sense, how are all the quantities in this class being calculated, and what is the total energy of a system, right? So, energy involves a lot of things. It involves kinetic, potential, the energy of the fluid, and work, and heat transfer, right? All of these things sum up to total energy, right? And so, we've already talked about kinetic, gravitation, or potential energy, so we're not going to talk about other things as well. So let me see. Yeah, this is a good one to start. So it says, when work is done to compress a spring, which is the first paragraph right here. When work is done to compress a spring, energy is stored within the spring. When a battery is charged, the energy stored within it is increased. And when gas or liquid initially at an equilibrium state is in an enclosed insulated vessel is stirred vigorously and allowed to come to a final equilibrium state, the energy of the gas is increased in the process, right? Would you guys agree? Is that if I sit here and stir water really, really fast, the energy in the water is not the same as it is before, right? Because it's absorbing the kinetic energy I'm putting into it, correct? I think that makes sense. So, and it says, in keeping with the discussion of work in section 2.2, we can also think of other ways in which work done on systems increases energy stored within those systems. This part, work related to magnetization, for example. That was some other one that we haven't talked about, but we're not going to. And it says, in each of these examples, the change in system energy cannot be attributed to change in the system's overall kinetic or gravitational potential energy as given by previous equations. The change in energy can be accounted for in terms of internal energy as considered next. So this right here, this is our next big definition, internal energy. So internal energy in this class is denoted as U. And that is a very important one because U is the second table value that you have learned in this class. The first one is specific volume. The second one is internal energy, which is this. And so these are the things that you will then have to look up in tables very shortly for your homework for next week. So internal energy and specific volume are the two concepts you have learned so far that are in tables. And we will look at the tables probably on Monday just to give you a better idea of what they look like and how to use them. So, and it says, in engineering thermodynamics, the change in the total energy of a system is considered to be made up of three macroscopic contributions. One is the change in kinetic energy associated with the motion of the system as a whole. Another is a change in gravitational potential energy associated with the position of the system, right? And then all other changes are lumped in internal energy of the system. Like with kinetic and gravitational potential energy, internal energy is an extensive property of the system, as is the total energy. Okay? And it says internal energy is represented by the symbol U, and the change in internal energy in a process is U2 minus U1. So this is essentially what they're saying is that the change of internal energy is delta U, or U2 minus U1. The specific internal energy is symbolized by U, or U bar. I don't worry too much about U bar, but we just deal in U's mostly, no U bars. And then it says, depending on whether it is expressed as a unit of mass or per mole basis. So we'll get, the ones in the table are on a per mass basis for U. And then it says, the change in total energy of a system is the following. It is delta E, so it could be also written as delta E. So here, let me scroll down a little bit. So delta E. So, oh yeah, it actually shows it right here. I guess it was because this was blocking it. So, E2 minus E1 is equal to U2 minus U1 plus kinetic energy 2 minus kinetic energy 1 plus potential energy 2 minus potential energy 1. So this right here is that first equation just summarized in deltas. And so what that says is, if you read from left to right, is the total, or the energy from state 1 to state 2, essentially the total energy of a system, is equal to the change in internal energy, the change in kinetic energy, and the change in potential energy, right? So if from one state to the next we gain a bunch of energy, obviously that is the total energy of the system, right? It's the difference between the two of them. So that is the equation. This is another big equation that you guys will need to know right here. So I would write this down, or at least remember what page it's on. It's on page 68 of our shadily obtained book. So, next one. Let me see if I can find something that's more important for us. Okay, yes, this is a good idea. So it says, a microscopic interpretation of internal energy by thinking of the energy attributed to the motions and configurations of the system molecules, or individual molecules, atoms, subatomic particles making up in the matter. So when we say internal energy, what I want you guys to think of is that it is not, essentially it's energy that the fluid has absorbed, right? So it is not it's not like, so let's put it this way. If you increase the temperature of water, right, from, like, let's say just room temperature water, 20 something C, or like 70 degrees Fahrenheit, whatever you might want to call it. If you have that water just staying out there, and then you increase the heat of it, let's say you increase the heat of the water to near boiling point, the internal energy of that water is now higher as a result of that, because that water now has more energy inside of it. It is absorbing the energy. It is taking it in. It's no longer low. It is now a lot higher by a magnitude of multiples, right? And so that is what it is. Essentially, it is it's all the fluid has absorbed all types of energy, whether that be kinetic, heat, all that stuff. And that's what it says in here. It says gas molecules move about encountering other molecules or the walls of the container. Part of internal energy of the gas is the translational kinetic energy of the molecules. Other contributions to the internal energy include the kinetic energy due to the rotation of the molecules relative to their center of mass, and kinetic energy associated with vibrational motions within the molecules. In addition, energy is stored in the chemical bonds between the atoms that make up the molecules. Energy storage on the atomic level includes energy associated with electron orbitals. Okay, so real quick, this stuff right here, you will not have to know. What I want you to understand is that essentially, let's put this in terms that aren't talking about subatomic particles and other things. Here, ready? Water here, energy go in, energy level go up, right? You see the point? So essentially, water at some energy level here, when there's some sort of energy added to it, such as like kinetic, potential, heat, whatever it may be, work, that this water's energy level goes up. It's sort of like, you at the gym, right? You're down here in here. Let me draw you guys after the pandemic. So this is you flexing. There's your very tiny muscles, right? Energy level really low. You put in a month, or you put in some more work, you put in some time, you put in some energy, then you end up over here at, big muscle dude, right? See the point? And yes, it does look like his arm is a flipper. You have not turned into an otter. So, this is the point, though, is that energy level low, you put in energy, it goes higher. It is absorbed, right? In some way. So that's what I want you guys to understand. This, nuclear spin, orbital states, binding forces. That's not important for us to know in this class. In this class, we deal with a more macroscopic view of thermodynamics. There are parts of it in this book that deal with the microscopic version, which you would actually be talking about things like that. But that's in a class that is graduate level that I did take. So it's not all that important for us right now. And I think you guys are probably happy about that. All right. So right here is where we will leave off for next time. And now we have to talk about the same things that we did about work, but in terms of heat. So the next time we'll be talking about heat transfer, which is different than work. So essentially work would be given as such like a paddle wheel spinning water. Heat would be like, for example, it's like right here. So essentially, a paddle wheel would be inside of here, right? And it'd be spinning it up like that, which is a mechanical addition of energy. Energy by heat transfer is essentially just the opposite. It's sitting on a hot plate, or it's, on your stove downstairs, right? And there's heat coming up through the bottom of it. That is the addition of heat in that sort of sense. So they are two different things, but they both transfer energy, which is what we're looking at. We want to know how to solve that initial equation right here in terms of all of these concepts. And now you might be wondering, you're like, well, wait a minute. How there's no work and there's also no heat transfer in any of these equations. That is because there's one further equation that relates internal energy to heat transfer and work, and it goes like the following. It goes work minus Q, so it's heat minus it's work minus heat is equal to U2 minus U1. So essentially the internal energy of the system is a representation of how much work or heat transfer that has been put into it. So that is the next part. And so essentially you find the heat transfer and you find the work using internal energy states. Or if you know the work and you know the heat transfer, you can find the internal energy states. But if you don't know the heat or work, you can find it using internal energy. So that'll be the next thing we do. And so we will finish this part of the chapter. We'll finish that part, and then we will end up going down here and to start doing more questions, because now we've figured out the questions. This is where we start here. So you see right here, you can replace them in different forms, and we'll get to those when we get to the next class. And I'm going to be posting a homework assignment probably tonight or tomorrow. And it will be due next, I think we're going to have it due Sunday to Sunday. And so, like I said, Sunday to Sunday will be very helpful because you guys can come and talk to me on the weekends. Do what you have to do. If you have any questions, I'll be more than happy to join the channel. But, so I know that's a lot of information that's been thrown at you now. But now we are starting to get into where it's being applied, right? All that stuff that I've been talking about basically for the last, 2 lectures is essentially background information to getting to here. Getting to this stuff. And then once you see how it's applied in a question, it will make a lot more sense to you, I promise. And we will work on doing more questions, so like practice questions probably Monday and Wednesday. And then if you need me to do an example, I'd be more than happy to. But let me go ahead and take attendance before you guys leave, and then we can have you guys enjoy your weekend.